This is part 2 of our discussion of orbital mechanics. Now, the very word orbit seems to suggest a path that is roundish, cyclic, repeatable. And we've been discussing satellites that are bound by gravity to a planet. But orbital mechanics also describes the paths of unbound objects, like a robotic spacecraft making a reconnaissance of a distant planet. And to describe those paths, we're going to have to go beyond ellipses. Let's start with a brief recap of Kepler's laws and the principles of orbital mechanics. To begin with, Kepler's first law states that the orbit of a satellite is an ellipse with the planet at one focus. So, to describe the shape of the orbit, we need to be able to describe ellipses. And an ellipse is basically described by two numbers. The first is the semi-major axis, which is 1/2 of the major axis, or large diameter, of the ellipse. And the second basic quantity is the eccentricity. It's a measure of how flattened the ellipse is from being a circle. A circle has eccentricity 0, but a very long, narrow ellipse would have an eccentricity near to 1. Kepler's second law says that a line from the planet to the satellite sweeps out equal areas in equal times. This means, of course, that in the parts of the orbit where the satellite is closest to the planet, it's moving more rapidly than when it is farther away. And Kepler's third law is the harmonic law, which states that if you have several different satellites in orbits around a given planet, the cube of the semi-major axis is proportional to the square of the orbital period for the satellites. And Newton was able to show that that was a consequence of the law of gravitation that he found. And we can sort of express that as what we call the Newton-Kepler 1, 2, 3 law, that g times the mass of the planet over 4 pi squared times the square of the orbital period is equal to the cube of the semi-major axis for all orbits of all satellites around all bodies. By the way, Kepler was the first to introduce the term satellite to describe a small body in orbit around a planet. This brings us to the key idea in orbital mechanics, that properties of the geometric shape of the orbit, like the semi-major axis and eccentricity of the ellipse, are related to mechanical quantities, quantities having to do with position and speed, force, energy, and so on. And by far the most useful relation that we have is a relation between the specific energy of the satellite and the semi-major axis. Essentially, if you know one of them, you can determine the other one. So this leads us to a tremendous set of mathematical tools, equations that relate the apocenter and pericenter distances, and the eccentricity and the semi-major axis, the specific energy of a satellite and its orbital period. And with these, we can find out all kinds of things about bound elliptical orbits of a satellite around a planet. The closed curves that describe bound orbits of a satellite around a planet are in fact the same curves that you get if you slice a cone by a plane. They're called conic sections. So if you slice a vertically pointing cone in a horizontal plane, you get a circle. If you tilt the plane a little bit, you get an ellipse. And all of those curves are the shapes of bound orbits, orbits where the total mechanical specific energy of the satellite is less than 0. So this raises an intriguing possibility. Maybe the trajectories of unbound satellites, the flyby trajectories and so on, are the other conic sections, the parabola and hyperbola that you get with an even more strongly tilted plane cutting the cone. These would be orbits for unbound satellites with energy greater than or equal to 0. And that's exactly the way it works out. We're going to call a trajectory an orbit, even if it doesn't go around the planet, even if it's just a bent flyby trajectory. And let's make a table. We have two types of bound orbits. There's a circle, where your speed is exactly the circular orbit speed. Your energy, of course, is less than 0 because it's a bound orbit, and the eccentricity is 0. More generally, you have an ellipse, where your speed is less than the escape speed, so that your energy is still negative, but the eccentricity can be anything less than 1. Now we consider the unbound orbits. A parabolic orbit is one in which your velocity, your speed, is exactly equal to the escape speed, and that makes your total energy, kinetic plus potential, equal to 0. And a parabola is said to have eccentricity equal to 1, just above the eccentricity of even the longest, skinniest ellipse. And then if you're going even faster, if your speed is even greater than the escape speed, then the shape of your orbit is a hyperbola. The total energy of the satellite is positive, greater than 0, and the eccentricity is also a number greater than 1. But that raises a question. How do we find the eccentricity for a parabola or a hyperbola? What does that even mean?
So our challenge is one of generalization, to find more general mathematical descriptions that not only apply to circular and elliptical orbits, but to these new unbound orbits, parabolas and hyperbolas.
Let's show what we mean by thinking about the eccentricity for an unbound orbit. Our idea is to find an expression for eccentricity that makes sense even if the orbit is not an ellipse, if it's unbound. So let's recall that for an ellipse, the eccentricity is 1 minus the paracenter distance over the semi-major axis. The problem is that an unbound orbit is infinite. It doesn't have a semi-major axis. This expression doesn't make any sense. But we can recall the fact that the semi-major axis is related to the energy of the satellite. The semi-major axis is minus gm over 2 times the specific energy. The specific energy, of course, is negative. But this would allow us to derive an expression that doesn't involve the semi-major axis, that only involves the energy. And so here's the expression. The eccentricity is 1 plus 2 times the paracenter distance over gm times the energy. And if the energy is less than 0, this gives you an eccentricity that's less than 1, like a circle or an ellipse. If the energy is equal to 0, then the eccentricity is equal to 1, a parabola. And if the energy is greater than 0, then this expression gives you something greater than 1, just what we need for a hyperbola. So, let's suppose we have a satellite making one of these hyperbolic flyby passes around a planet, and the eccentricity is given by the expression that we've already found. Now, because this is an escape orbit, this is an orbit that allows the satellite to escape the planet, then it has a value we call v sub infinity, the asymptotic speed. That's the speed the satellite has when it's a very great distance away from the planet, either before or after the encounter. And that asymptotic speed is related to the energy of the escape orbit by the fact that that energy is just 1/2 asymptotic speed squared. So that means we can write a second relation, also useful, that relates the eccentricity of the orbit to the asymptotic speed, the speed very far away from the planet, and the distance of closest approach, the paracenter radius.
Let's consider an important application of these ideas to spaceflight. We'll talk about the hyperbolic trajectory of a spacecraft that is flying past a distant planet.
So here we go. Very far away, the spacecraft is flying at its asymptotic speed, and then it gets close to the planet, and two things happen. It speeds up, and also its path is deflected. And then as it leaves the planet, its it slows back down to its asymptotic speed, and its trajectory has been bent through an angle which we might call beta. That's the bending angle. So the distance of closest approach is r sub p, the paracenter distance. And we notice that for this to work out, the paracenter distance had better be bigger than the radius of the planet. Otherwise, the spacecraft has simply crashed into the planet. And the eccentricity is 1 plus rp times asymptotic speed squared over gm. But we really haven't said what the eccentricity means. In fact, what the eccentricity tells you is it tells you how much the hyperbola bends. It tells you something about that bending angle. And in fact, the formula is this, that the sine of beta over 2 of half the bending angle is just the reciprocal 1 over the eccentricity. And that's a beautiful relation. So for example, suppose my eccentricity was 1.5. That means that the sine of beta over 2 would be 0.667. 1 over 3 halves is 2/3. And by taking the inverse sine of both sides of this equation, I get that beta over 2 is 41.8 degrees, which means that beta, the bending angle for this hyperbolic path, would be about 83.6 degrees. The hyperbola would be bent almost at a right angle. Let's suppose we're sending a spacecraft on a flyby trajectory past the planet Mars. Now, the planet Mars has a mass about 1/10 the mass of the Earth, and so g times m is about 4 times 10 to the 13th in MKS units. The radius of Mars is about 3,390 kilometers, a little over half of the radius of the Earth. We'll suppose that the asymptotic speed, the speed with which we approach Mars from a very great distance, is 4,000 meters per second. And the closest approach to the surface of Mars is about 10,000 kilometers, which means that our paracenter radius is that plus the radius of Mars, 13,390 kilometers. Actually, these particular values are quite close to the real values for the Mariner 4 encounter. You'll remember Mariner 4 was the first successful flyby mission past Mars, and in 1965. Okay, so what is the eccentricity of the hyperbolic path of Mariner 4 past Mars? Well, we can calculate that quite simply. We can just use our expression that involves the asymptotic speed. We can put in the values, making sure that we're using meters, kilograms, and seconds for our units, and we get that the eccentricity is 6.01, a very, very flat hyperbola indeed. Well, what does that mean? That means that the bending angle, the amount by which Mariner 4's trajectory was bent by the planet Mars, is only about 19.2 degrees. It's not bent very much. So what's the maximum possible bending angle? In other words, suppose we are still approaching with the same asymptotic speed, but we want to bend our trajectory as much as possible. Well, to have the maximum bending angle, we want the minimum eccentricity. And the minimum eccentricity means we want to have the minimum paracenter distance. And the minimum paracenter distance would be the radius of the planet. In other words, for maximum deflection, we want to just barely skim the planet, just barely clear the planet's surface. Okay, well, where does that leave us? Well, if we find that minimum eccentricity by substituting the planet's radius for the paracenter radius, we get an eccentricity of 2.27. And that means that the maximum possible bending angle for a hyperbola around Mars, approaching at 4,000 meters per second, is 52.3 degrees. So here's an exercise for the interested student. How close would we have to get a little bit less than this, to have a bending angle of 40 degrees? It's not hard to figure out.
Circles, ellipses, parabolas, and hyperbolas, and the mathematical machinery we found to describe such trajectories are the basic building blocks, the basic toolbox for understanding orbital mechanics. Next time, we're going to talk about using rocket propulsion to change orbits. Perhaps we're in an orbit about a planet and we want to fire our rocket motor to escape. Or perhaps we're talking about a spacecraft coming in from distant space and wanting to fire its rocket motors to go into a circular orbit around the planet. Or perhaps we simply want to go from one bound orbit to another. All of these maneuvers can be accomplished with rocket propulsion, and that is our next item of business.